Hello everyone, my name is Đức Việt Lê and I am a PhD student at Purdue University. Today we're going to present our work on enabling oblivious accesses to Bitcoin and other UTXO-based blockchains. So this is collaborative work with Adil Ahmad, Mohsen Mineh, Aniket Kate from Purdue University, Lizzie Hurtado from National University of Columbia, and Byung-Yong Lee from Seoul National University. So first to begin with, uh, some motivation of this work is, as we all know, the size of the Bitcoin data has become too large to store in a resource-constrained device like mobile phone or personal laptop. So as March of 2020, the size of this database is around 269 gigabytes. So the current solution to address the storage issue is a SPV client. The design of this solution relies on Nakamoto's idea in his white paper, and it later standardized in Bitcoin Improvement Proposal 37. So in this setting, the thin client or the resource constrained client have to rely on other full client for fetching transaction information and transaction data. In this slide, we give an overview on how today's solution works. The today's solution rely on the use of Bloom filter. In particular, when a thin client wants to fetch some data from the full client, it first loads all the addresses and transactions of interest into the Bloom filter. The Bloom filter later sends in plain to the full client, and upon future request from the thin client, the full client will use a filter to scan data and send back only transaction and block that match the filter along with the Merkle proof and everything. However, in AXAP 2014, Arthur Gervais and other researchers from ETH Zurich have shown a network layer attack on this approach. In particular, by collecting multiple filters from the same client, the adversary can guess the addresses belong to the SPV client with high probability. So a natural solution for this approach is we need a full client that offers private accesses to the thin client. So in particular, when a thin client sends a request to the potential malicious full client, it will answer the request with some response. However, it should not know what data did the thin client fetch. So one solution for this is to use private information retrieval techniques. However, to our limited understanding, pure cryptographic approach are not yet scalable for this kind of problem in terms of computational overhead and bandwidth overhead. So another approach is one can use Oblivious RAM and trusted hardware to offer a generic PIR solution. In particular, the thin client can assume trusted hardware reside on the server, and this trusted hardware will perform access on the encrypted database on behalf of the thin client, and these accesses on the trusted database will be protected using ORAM. So in the next few slides, we will explain what ORAM is and what trusted hardware we use for this work. So ORAM is a cryptographic primitive first introduced by Odette Garage to hide data access pattern of a program. There are several design paradigms for ORAM, but in this work we use two constructions of tree-based ORAM, which is part ORAM and circuit ORAM. So in ORAM testing, there are a client and a server. The server stores data blocks in a binary tree structure. The client maintains two local data structures, which are the position map, telling which path in the tree the block ID the block belongs to, and the stars is used to store data retrieved from the server. In this example, we explain how part ORAM works. Let's say the client wants to fetch block ID number 4. It look at the position map and identify block ID number 4 reside on part 3. It later requests the server to send back part 3 to the client. It stores the whole part in the stars, decrypt every block in the stars, identify the block number 4 and perform either read or write action on the block. After finishing the action, the client now needs to re-randomize the position of the block by assigning the block a new path. In this case, let's say it assigns block ID for part 1. Then, therefore, block 4 will need to be rewritten at the root node because, as you can see, the only overlap between part 1 and part 3 is the root node. So it will request the server to store this new block, store this new path into the server. So all the logistic and data structure implemented on the client side are known as the ORAM consulates. And the tree-based ORAM access can be generalized into a combination of two operations, read path and eviction. So the main idea of this work is we use ORAM to hide the access pattern of thin client on the blockchain data. Next, we discuss about trusted execution environment. For this work, we use Intel SGX as our instance for T. There are two important properties that we need from Intel SGX. First is the attestation mechanism. So Intel SGX allows a client to remotely authenticate the SGX. Secondly is the code isolation. So the Intel SGX can set aside adjusted memory regions known as the enclave for code isolation. The SGX processor makes sure that no other program can access this memory region. So for this work, we argue that we can implement ORAM controller inside the enclave, and the clients can remotely authenticate this Intel SGX, and the Intel SGX will perform ORAM accesses on the behalf of the client. Now going back to the ORAM architecture we mentioned before, now they're no longer the client. The client now becomes the enclave, and the server now becomes the untrusted memory region. However, combining ORAM and T as a solution for the blockchain introduce several technical challenges. In the next few slides, we will explain what are these challenges and how we will address them. So the first challenge is the storage overhead. So using ORAM as it is incurs a constant storage blowup. In particular, that if we use the parameter suggested by the paper, we will expect 8-time blowup for part ORAM and 4-time blowup for circuit ORAM. So if we just store the Bitcoin blockchain into ORAM tree structure, it will result like 1.6 terabyte of blockchain data. To address the problem, we need to look at individual transactions of Bitcoin. Bitcoin transactions are formed by different data inputs and data outputs. When a client wants to send money to other recipient, it creates transactions using output that belong to it and that are not used as input before as new input in the new transaction. New output now encodes the data of the recipient addresses and the value of the money it wants to send. Outputs that are not used as input before is called the unspent output. They are necessary information for client to determine the balance and form new transaction. And the collection of these unspent outputs is called the UTXO set. For this work, we argue that T3 should only maintain this data set via Oblivious update, and T3 should only provide thin client with Oblivious access to this UTXO set. So the size of this data set is only around 2.8 GB at the time we tested our prototype of our implementation. Therefore, the storage blowup is 24 GB for part ORAM and 12 GB for circuit ORAM, and which, in our opinion, is acceptable for the implementation of the system. So the second challenge is a lack of concurrency in traditional ORAMs. In particular, we recall that an ORAM access is a combination of two operations, read path and eviction. The eviction procedure is a procedure that causes writing on the tree. Right? So therefore, if there's a new client send a request during the eviction procedure, their request will get blocked by this eviction. Similarly, in our setting, a Bitcoin network generates a new Bitcoin block every 10 minutes. So the new Bitcoin block can generate up to 1,000 of ORAM update requests. So if a client sends a request during this update, their request will get blocked by this update procedure. So to address the problem of concurrency, we introduced two ORAM trees, one read tree and one original ORAM tree. The idea here is to split an ORAM access into two operations, into two different trees. So read part perform on the read tree, and the evasion perform on the original tree. And we require the system to synchronize these two trees every 10 minutes, at least for Bitcoin. And this allows concurrent access on the read tree, and why introduce a non-blocking evasion on the original tree. So on the security of this proposal, right, we argue that for a rational SPV client, for each address, it should only request one ORAM access during the in an interval of 10 minutes. Right? However, even though if the SPV client is not rational by using multiple requests for the same address, the system still ensures the privacy of the client by synchronizing the two trees every 10 minutes. On the efficiency side, because we allow parallel accessing on the read tree, we improve the latency from the perspective of the SPV client. The third technical challenge is the limitation of Intel SGX on the size of the trusted memory region. So the size of the processor reserve memory is limited to around 96 megabytes. So what it means in our system is that the size of the position map and the start cannot exceed 96 megabytes. So therefore, the naive use of ORAM will quickly cause the PRM to running out of memory. So we note that allocating more memory is possible, but the performance will significantly decrease. So, however, this problem has been studied in the ORAM literature. The solution here is to use recursive ORAM construction. The idea here is we can reduce the size of the position map by storing the original position map into another ORAM structure in the untrusted memory region. And by keep doing that, we can reduce the we can keep doing this until the size of the position map fit the unclaimed memory, and this is what we did in our system. So the fourth technical challenge is we need in T3 we need to tell T how to map Bitcoin addresses into ORAM block. The first naive approach is to use Bitcoin address as ORAM block. The problem with this approach is that the size of the Bitcoin address is too big to store in the position map, and the size of the position map will become too large for the unclaimed memory. The second approach is to deterministically hashing addresses into ORAM blocks. Again, the problem with this approach is that if the mapping is known to the adversary can always overflow the block with its own output, and the outputs of honest user will get discarded. So to address this challenge, we use a pseudo-random function to map Bitcoin address into ORAM in T3. However, there is a secret key that fitted into the pseudo function that is generated and kept secure by T. And at a high level, this means the mapping between Bitcoin address and ORAM block is kept hidden by T. So in our paper, we propose a different mapping for different trade-offs in terms of storage, and we refer readers to our paper for the discussion. However, it's still to introduce two problems. First, as we mapping something from bigger domain into something of smaller domain, we introduce collisions. But we argue this is a standard max load analysis, and one can always show that ORAM block will have less than certain number of outputs with overwhelm probability. The second problem is that some addresses inherently have more output than others, and how would we address this issue? So we did some analysis on the UTXO set, and we found out that 92% of addresses only have up to 2 outputs. So in our implementation, we therefore limit the number of outputs for each addresses to only 2 to cover 92% of all users. So we also note that choosing a different number of output is possible, but there will be some trade-off in terms of storage, blow up. Again, we refer to our paper for this trade-off. So to put things together, we have an overview of our system. When the SPV client wants to perform a read access on the UTXO set, it connects to the server, perform a remote attestation with the Intel SGX, and establish a secure channel with this SGX. And any future request from the client, the read request will be split into 2 different operations. Read part performed on the read ORAM tree, and eviction performed on the original ORAM tree. As we mentioned before, by doing this, we allow parallel accessing of the RISC-1 ORAM tree to improve the latency from the SPV client. On the update side, the Bitcoin network is the only party who perform updates on the original ORAM tree. Therefore, when a Bitcoin block arrives from the network, the enclave needs to verify the proof of work of this block by using its own storage of a Bitcoin block header. After verifying the proof of work, it performs a batch write on the original ORAM tree. Once this update is finished, the system will synchronize these two trees. We also note that during this update, the system is still able to handle requests from clients. And this is an overview of how our system works. So for the evaluation of the system, we tested the performance of our prototype on two different constructions of ORAM, part ORAM and circuit ORAM. So this is the performance of the original ORAM access or the eviction procedure. And this is the performance of RISC-1 access. Because there is no eviction on the RISC-1 access, the performance of these type of accesses better compared to the performance of the original accesses. Moreover, by having two different trees, read tree and original trees, we allow concurrent read on the RISC-1 tree, and it is a performance of the concurrent RISC using different number of threads. So in this figure, we compare the performance of our system with the current SPV clients using four positive rates. Moreover, we compare our system with Oblivious database, which is a concurrent work that also uses ORAM and T for the blockchain setting. However, in the system, they only use non-recursive part ORAM and T as it is. We re-implemented the system using the parameter from that paper. And we show that if the system using recursive part ORAM, the performance of the system will be significantly improved. In this figure, we can see the performance of T3 is shown in the dashed black line and blue line. And the performance of our system is better due to the use of RISC-1 access, which does not require eviction. So in this figure, we compare our system with SPV client in terms of bandwidth overhead. In the current SPV client that use Bloom filter, due to the four positive rate, there can be additional irrelevant data sent by full client. So as you can see, if the higher the false positive rate, the higher the communication cost for the full client and the SPV client. And since our system relies on the SGX to extracting relevant data, the amount of data need to be sent by the full client is significantly smaller. So in conclusion, we developed a system designed that supports large-scale Oblivious accesses on the utility-based blockchain by using Oblivious RAM and trusted execution environment. We also address several challenges of the naive use of ORAM and T for blockchain setting by introducing concurrency design and the use of recursive ORAM. We also provide an prototype implementation of our code in the following link, and that concludes my talk. Thank you for listening, and I am happy to take any questions.